So our next speaker is our own Alex Giladi. He is a distinguished architect at Comcast, and his talk is entitled Massively Parallel Encoding.
Thank you, Yasser and Dali. So I think we'll get a pretty unique result here because we'll run ahead of the schedule and not go behind it, as Kalyan kindly covered a lot of the same ground. So what I wanted to talk about is how do we take X265 at really good quality, and how do we run it in parallel, how do we speed it up? So first of all, a little bit of motivation. As Gary said and showed, we have growing codec complexity. We started with 16 by 16 macro blocks in MPEG-2. We have 64 by 64 quad tree in HEVC, and we're getting into three-digit numbers by now. Same with motion estimation and so on. This costs a fair amount of cycles. And yes, we have Moore's law. Yes, we have hardware acceleration. And yes, we have good software implementations. But we're still stuck with a pretty slow encodes for Ultra HD content. Just as an anecdote, you can encode an Ultra HD movie in about 1 to 2 days. Then this is actually serious. So right now, according to Ultra HD Forum, there are about 250 known Ultra HD titles. So this is not that bad, but it will become worse as there is more production in 4K. So why do we need parallelization? First of all, we are strongly CPU bound and even core bound rather than complete CPU. Then, to make things worse, newer CPUs improve amount of cores, but not improve speeds. And lastly, 2 days of turnaround time is not really a good thing. You want to have your movie transcoded relatively fast, egressed relatively fast, and be available to your subscribers fast. So you can. The first thing everybody mentions is fine-grained parallelism. There are codec tools that were already mentioned here. There is wavefront parallel processing in HEVC, which goes down to CTU level. There are more coarse tools that exist in AVC and HEVC, slices and tiles. On the implementation side, you can try encoding a frame per thread and then doing inter-process communication to go and keep the rate control well informed about the state of the buffer. So all of these work if used in moderation. So large amount of slices, it both creates very interesting artifacts and coding inefficiencies, especially in AVC. As an anecdote, I saw an encoder that used more than 10 slices to get enough parallelism, and if you turn the rate down sufficiently, you could actually see the lines that separated the slices. So going back to the issue of good things used in moderation. So I couldn't resist putting this picture here as an overclocker. This is the wrong way of speeding up encodes. This is a recent Intel processor running at 6.1 gigahertz with liquid nitrogen. So this is awesome, and I doubt anyone sane would put this into a data center. So then this was a brute force approach. Let's try another brute force approach, and let's do massively parallel encoding. Let's break the video into multiple chunks and encode each one of these chunks separately. Note that chunk is an overloaded term in adaptive streaming. This is just a piece of video. This is not something that is a single segment. And actually, if possible, I would rather avoid having equal duration. So you are encoding them separately. You are stitching then the chunks together as a rendezvous process after all the jobs are done. In case of things like MPEG-2 transport stream, single file, -VOD profile, you are actually physically touching the files. In other cases, this is only conceptual. You output discrete segments, and you're stitching them by creating a manifest, an M3U8 in HLS, an MPD in Dash. So the benefits are pretty simple. You get better CPU utilization, and from what we've seen empirically, and if a high-quality instance of process of X265 does not saturate a large enough system that has sufficient amount of cores. So you're better off with multiple processes. You get to your CPU saturation. Lastly, as I already mentioned, turnaround time. If you put a sufficient amount of servers to this task, you can transcode a movie in an hour or less than an hour. It's just about the size of the chunk and the amount of money you are willing to pay to Amazon, Azure, or anyone else. An issue that was mentioned before. Whenever you try something that is several independent encoding jobs, you run into a problem that HRD, the hypothetical reference decoder, is a serial process. So if you start encoding uninformed, you start from some value. For instance, both X264 and X265 assume that your buffer is 90% full. You start with this, you run with this, and you don't really know at which degree of CPB fullness, of buffer fullness, you will end up. So here is a pretty simple illustration of what happens and what the encoder thinks what happens, and what you will see what happens when you see a problem and open the stream in the analyzer. So the first chunk starts at its, let's say, 90%. It doesn't look like 90%, but believe me. And adds somewhere else probably higher than that. The second independent encode starts at exactly the same thing. It's just the default in both X264 and X265. And it doesn't realize that there is actually a small drift developing that goes upwards. And if you have a sufficient amount of these independent encodes, you may develop a drift. So again, for every problem, there is a brute force solution. And the simplest brute force solution here is let's go and tell each encoder, where do we start fullness-wise? Where do we end fullness-wise? So this actually works, and provides good results. Again, as every solution, it has its own problems. Basically, if you go and start underutilizing your buffer at the very end of your encode, you're obviously going a little bit down in quality. So you have to be careful in terms of what you are doing. So just recently, reading the commits to X265, I noticed that there is an interesting alternative solution, which seems to be encoding some amount of extra frames on both sides of your chunk, and this way arriving at a better estimate of your fullness. So this is an interesting solution. It may have its problems in terms of mismatch, especially in context of different bit rates applied to different to different chunks. But still, it's a pretty interesting thing to try. I unfortunately haven't. So how do we create chunks? The simplest thing is let's say we have a GOP that has 48 frames. Let's take this GOP and encode it independently. So it's probably the worst way of approaching this. First of all, you don't want to cut your scene in half and maybe encode one part of the scene at a much higher quantizer or much lower bitrate than the other. You'll immediately see the result when you stitch. That's why we want to avoid these stitch marks. And one of the ways of doing this is just reducing the amount of them. If you have something like this showing up every 2 seconds, this is far more annoying than having these occur every minute or two. And then if you go and try encoding an integer amount of scenes, basically doing scene change detection, and then creating these chunks, not necessarily equal in number of frames, but containing complete scenes, then your some amount of loss of efficiency will be masked by the fact that you have a scene change coming immediately afterwards. Another probably last note on this. So encoding initialization takes time. If you saw, for instance, Kalyan's presentation, there are a lot of interesting things done with multiple threads that you actually have to start, and it takes them time to get started, and to start running, and so on. If you go with very small durations of chunks, you are paying a disproportionate amount of resources for the startup and for the tear down. We noticed this kick in, for instance, at the level of even 15 seconds. Now to something completely different. How do we actually try speeding things up as opposed to reducing the turnaround time? So how do we avoid liquid nitrogen? If you think about the specific case of adaptive streaming, you are encoding multiple representations in Dash terminology, multiple resolutions and multiple bit rates. Now, the reason why you are doing this is that you can adapt this way to the bit rate, and it actually doesn't matter if to that degree if your TV goes and upsamples your 720p to 4K, because that alternative, because of your network conditions, is showing a blank screen. So basically, if you think about it as something that is scaled, the objects are the same, the object boundaries are the same, the motion field is the same. Basically, my talking head looks the same in 360p and in 4K. If you go and encode every bit rate separately, you are missing this. You are missing this part. You are making the same decisions on different resolutions, or even on same resolution, but different bit rates. And you may be better off reusing this information. So conceptually, this is not something that is new. People who remember how MPEG-2 encoders were built probably remember hierarchical motion estimation, where you start at quarter resolution, refine at half resolution, refine at full resolution. Here we're doing something very similar. We're running a low resolution encode. That is actually a full encode and can be egressed and can be played. Then we output two things out of it. We output the log of each of all of its decisions at the CTU level. What is the quad tree structure? What are the motion vectors, and so on and so forth. The other part is let's go and output frame types. Given these, we can construct a tree that reuses the information and the decisions made at lower resolution encodes at high resolution encodes. So there is some work, some recent literature that discussed this. Surprisingly enough, people went in a completely different direction and started from 4K resolution and then tried speeding up lower resolutions. While this is a valid approach and it seemed to be working, the benefits of this are pretty low, so we didn't really consider this. How does this thing actually work? And actually is thanks to Kalyan and at some earlier point in time, Tom here. It is implemented in X265, and X265 lets you output and input analysis files which contain all the decisions and go and improve on the results. So what we can do is either reuse just the frame types, and this holds for any single resolution, or use things at the CTU level, as it is implemented right now in X265. This is only for dyadic resolutions. So if you have 2n by 2n resolution, you can use prediction coming from either n by n or 2n by 2n. You cannot use 1.5n. And then we found that using the highest bit rate of a resolution for prediction typically gives a better result. And our speculation that may or may not be correct is that at higher bit rates, rate distortion optimization doesn't cause you to take something that is not optimal from the or significantly not optimal from the distortion standpoint. Now, this is what is implemented right now, and two interesting directions would be, since we have a multiple amount of codecs, and it's pretty hard to find a codec that is efficient and playable on all devices, we're stuck with supporting multiple codecs, and you probably can get, for instance, a significant improvement in HEVC encoding speeds if you go and interpolate from HEVC to HEVC. There are people who did the other direction as well already. Another thing that has a payoff, but probably less, is cross color space prediction, because again, the objects are exactly the same. My head hasn't moved, but in one case you can see whiter white than in the other. On the other hand, you cannot sell typically a movie that is only HDR, and you cannot get it in SDR. So if you combine them, you can probably gain some more efficiencies. So an example, let's take Apple's HLS ladder that they designed for 10-bit HEVC. It has 12 steps and multiple resolutions multiple bit rates per same resolution. And if you look at it, most of the resolutions are multiples of 2. I apologize for the typo here. Instead of 540p, it was supposed to be a 2K resolution. So what we can do is we can go and run 360p as normal independent encode, then extract both CTU level analysis and frame types out of there, and feed resolutions that are not an integer multiple with just frame types. And the reason for this is you end up with perfectly aligned frame types. You can pull off things like variable GOPs and not worry about alignment, and it gives you a few % of speed up. Then once you are in the area where you have multiples of 2. So you take 360p, you reuse things at CPU level at 720p, you refine this and reuse 720p analysis in 4K, sorry, in 2K. Same way, you get the 360p frame types for 540p. 540p resolution outputs analysis that is reused in 1080p. 1080p outputs analysis that refined analysis that is used in 2160p. Now, one thing that may have not been clear, if you go and reuse the analysis verbatim, what you'll get is a huge speed up and a drop in quality, and probably you don't want to pay this amount for your speed up. What we need to do is when we're scaling the resolution, when we're scaling motion vectors and quad tree structure, we need to go and evaluate new options that may have not been available. As a very simplistic example of what you can do is you can take a motion vector, you can scale it, and then you can start your motion estimation from this value as an addition to other predictors. Chances are that it's a pretty good predictor, and your motion estimation will run much faster than before, unless you are doing an exhaustive search, in which case you probably don't care about speeding things up anyway. Beyond hand waving, a little bit of numeric results. So we took 2 5-minute pieces from 2 different NBC movies, and we ran them under the same very slow preset, either as standalone 4K encode or as an encode that actually reuses information. There are several levels that are implemented in X265. Some are reusing more information, some are recalculating more, and an interesting mode that is dynamic switches between the different approaches based on the content. Now, what we got is a pretty significant improvement, up to more than 2.4x, and the price and quality for this turned out to be actually negative, using the SSIM plus metric that Professor Wang referenced earlier. We're gaining about something like a quarter to half of a GND. In case of weighted PSNR, it's a little bit worse. We're gaining about quarter to third dB in terms of BD PSNR. So quality improvement is marginal, but consistent, and the speed up is pretty significant. And the speed up is actually the reason for the approach. So how do we combine the two? Actually, things are falling together in a pretty comfortable way. We're creating a larger chunk that runs in parallel on some AWS instance or on some in-house server. We have everything that is frame aligned. We don't need interesting means of fixed GOPs to make sure that our segments are actually aligned. And again, this is something that works well with the new overlapping chunked encode mode that X265 just added. Last two slides, probably a segue to Yuri's talk in a few minutes. We may want to have constant bitrate, and this is what a good part of this town has been doing for a long time, just setting bit rates that are set in stone for all content, or we can do consistent quality, in which case we're allocating bits according to content complexity. This is called content adaptive encoding and was popularized back in 2015 by Netflix as per title encoding. HRD forum mentions about 40% bitrate savings mentioned. And the reason why I'm actually mentioning this in this context is that hierarchical encoding works really well with this, because you start with your lowest resolution. If you go and do some amount of feature extraction and apply machine learning to this, things actually work fairly fast. And then, given this lowest bitrate encode, you are able to guess the bitrate for higher rungs of the ladder at a relatively lower complexity. And there is a very interesting paper from YouTube, I think back from 2016, that described this approach. If you want to go this way specifically with X265, the zone's parameter is your friend. You can cause from command line. You can convince X265 to switch at GOP boundaries from one QP to the other, or from one bitrate to the other. So that's all, and I think we still have some amount of time for questions.
Okay, thank you, Alex.
Thank you for surviving the talk.
Okay. I guess we have questions, so I'll go ahead and...
Just a clarification, great talk, Alex. You actually saw a SIM plus gain. You showed negative numbers in that chart,
Yes,
but
so this is gain. So this is gain. This is not loss.
Okay.
Just to repeat the point, we're actually improving quality, not something that justifies the use of the approach just for quality improvement, but it's a nice thing not to get quality for free when you are speeding things up by a pretty significant amount. So
Okay.
we have to give credit for this to Kalyan, the previous speaker, who worked on this a lot.
Is that a technique you plan to apply for VOD or also live?
Right now, you cannot really apply it for live because you expect to finish one encode before starting the other. It's pretty easy to, if you are, in your case, an encoder developer, it's pretty easy to port this into real time. You will probably pay a little bit with latency because you want to run your first encode and then reuse its information in high resolution encodes. But especially if you are talking about 4K60, you can probably do this.
Yeah, thanks.
All right.
Alex, if I understood correctly, the chunking, you use SIM detections to do domain chunking?
You can live without it, but you are much better off with scene change detection running first.
My question is that if if you know about the, say, segment duration in streaming, does that help in terms of the chunking decisions you do, especially if you apply content adaptive encoding, because with the content adaptive encoding, you try to achieve the same quality for different segments at least.
So this is actually the other way around, because chunking, the hierarchical approach and frame type reuse let you have aligned segments by virtue of having properly placed IDR frames in more cases. Given this, you can go and have good use segment timeline or use segment indices, and have the effect that you were talking about.
But you allow the different segment duration.
You allow different segment durations. And this is actually something that helps you in more cases.
Okay, let's take time for one more question. Anything out there? Okay, thank you.
Thank you.